Hello, everybody. How are you doing? Narrowly Berry Jr. back for some more Science Hour. And we'll do some relativity. We'll continue with that. And we'll continue with where we left off before with the light clock. So be sure to drop a line if you have any questions or just let me know you're here. Discord if anybody wants to join and ask questions there. Not necessary. And we'll go ahead and get started. So this is where we were last time. We left off with looking at the light clock, looking at how the light went through a longer path from the observer's position on the ground compared to the observer on the spacecraft. And this is our textbook that we're looking through, Physics 3, from the free textbook that we can get online. And this is the actual illustration there. So what we'll do is continue from here and look at how the gamma term is derived. So when we're doing transformations between one reference frame to another, there's this gamma term here. And actually, hold up, lambda. This gamma term here. And this gamma term is basically what we utilize to make those transformations. So we'll go ahead and look at that and see how we can derive that and go from there. So let me make this window a little bit more expansive. All right, here we go. So going from the light clock, recall that the distance that the light travels in the frame of the spacecraft, they're going to be shorter than the one that it travels from the perspective of the onlooker on ground. So again, the light goes just up and down right here. You can see where my mouse is there for the person on the spacecraft. And the person watching, or they're able to follow, let's say, 1 photon of light, it will take this path here. So what we did was we called this distance at the bottom L, and we, by convenience of the math that'll come later, it's easier to break it into 2 instead of calling it 1 long L. So basically half the distance is L as it goes up, half is L when it comes down, and 2L is its entire length. And if we keep in mind that the spacecraft is actually moving along a trajectory, so 2L is actually the distance that the spacecraft travels. So the spacecraft with the light clock on it actually travels a distance 2L in the time frame that we're talking about. And if we look at the light actually travels from its perspective on the ground, but then from the onlooker that's not moving with the clock, the light travels S and S. So we can see that the light travels a much longer distance when looking, when it just travels up and down for the person that's on the spacecraft. Now, the definition for time dilation there says time dilation is the lengthening of the time interval between 2 events for an observer in an inertial frame that is moving with respect to the rest frame of the events, which is the frame in which the events occur at the same time. So the spacecraft is the frame where the events occur at the same location, because the light from the perspective of the astronaut. So looking at the astronaut again, the astronaut is just there. We look at the frame of the spacecraft, the mirror is just stuck there. So, if there were no windows on the spacecraft and the spacecraft is moving at a steady speed, it'd be just like they're standing still and the mirror is just going up and down. The light is just going up and down right in front of the astronaut. Whereas the person on the ground, can see the spacecraft, for instance, crossing the sky. So this makes from the perspective of the spacecraft, person is moving, right? So basically, if we uh, suddenly opened up a window on a spacecraft while it was passing the Earth, it could look from the people on the spacecraft as if the Earth is moving by in the opposite direction at the same speed that the spacecraft is moving. Since the experiment we're talking about is on the spacecraft, we'll call that the stationary frame, which means it's proper time, which means everything is happening at the same location in the spacecraft, and the location that's moving relative to that, to the person on the ground, is going to be time dilation, because the event, basically the light emits here at this spot, but then the light goes back to the receiver at this spot. So it happens in a continuum of distances from 0 to 2L, as we can see on this diagram for the person on the ground. So the event, which is the light clock, does not happen in the same location. So the observer on the ground is going to measure time dilation, is going to measure a longer period of time. And we also went to the S equals B squared plus L squared by simply making a triangle out of the L, D, and S here. So the book says here, the lengths 2L and 2S are respectively the distances that the pulse of light and the spacecraft travel in time t in their earthbound observer's frame. So basically we're using a frame from here to here, and this is our change in t. So basically the change in t is going to be the frame from which we see the event happening at different locations. One location this happens, at another location that happens. There's going to be our change in t, not tau, just regular t. The length d is the distance that the light pulse travels in time tau, change in tau, the astronaut's frame. Right, so it gives us these three equations, and this is what we're going to solve. So we have 2s, which is the distance that the observer on the ground sees that the light takes, s going up and s going down, equals c, because it's moving at the speed of light, and change in t, because the person on the ground is measuring that time, is looking at the spacecraft move. We have 2L, which is these two distances here that the spacecraft is moving straight, equals v, which is the speed of the spacecraft, change in t. Because again, the person on the ground is measuring the spacecraft going at a certain amount of time. It's taking a certain amount of time to get from place A to B. And the light is moving so fast that from the perspective of the ground, the light goes up at an angle here, bounces down at an angle there, and basically runs back into the spacecraft at that point. So basically the idea from the ground, the perspective is like a football that's being passed, like somebody's running and throwing a football up and catching it. That's basically what we're seeing, right? And the person throws up the ball and catches the ball at different locations. And then we have the frame of the actual spacecraft, in which everything is happening in the same location. The light just goes up and comes back down a distance d up and d down. So the full time distance of light travel is 2d. And the person on the spacecraft, since we're using the distance on the spacecraft, the person on the spacecraft measures the speed of light as the speed of light and measures it going change in tau. So tau is going to be the time that's measured by the person on the spacecraft, which is again the time that's measured when everything is happening in the same location, because you're moving with the event being a light clock. So now we have these three equations here. And it says that, note that we use Einstein's second postulate by taking the speed of light to be c in both inertial reference frames. So what it's referring to is, if we look at this, right, if this was, let's say, a football, right, like if it really was a football, and we measured the how long it takes to travel, how fast it goes, we can really see that the football going in this direction has to go faster than this one because it covers more speed in the same length of time. So basically, if this person throws the ball up and throws it down here, standing still, it just goes up and down and that's it, right? If the person is running and he throws the ball up at the same vertical speed, we still have the same vertical V, but the running would actually add some V this way. And we haven't, I can't remember if we talked about this specifically, but we can in more detail another time. But vectors can be added together in vector addition. And what will happen is, and technically this arrow will be this long, and this arrow will be this long. And the speed of light here would actually be the vector addition of the upward speed and the lower speed. So let's say, for instance, the person throws the football up 1 meter per second, and the person runs 1 meter per second. This would be the vector that ends up being the speed the actual ball takes. So in our example, that will be S. So we'll do the same thing and we'll call it S. So if we was to get the combination of these two velocities, throwing the ball up and running with the ball, we would have to basically uh, look at it like this, if it's a bit clearer, which means I can actually make my arrow here a bit more accurate. And this is basically the addition of two vectors, which is basically what they call the head to tail method. Right? Just took the head of one arrow, put it at the tail of the other arrow, and where they end up pointing is actually the addition of these two. Another way we can do it is geometrically. So we can simply use the same equation that was used before and say s squared equals 1 squared plus 1 squared, which equals 2. So s equals the square root of 2. So let's see what the square root of 2 is. It should be something like 1.4 something. I'll put it in the calculator to be sure. We have 2 square root, yep, is 1.414. So as we can see, when the person is running with the football and throwing the football up, the football actually goes faster than any one of the individual vectors, right? And it's just the nature of vector addition. Even though the person is throwing the ball up at the same speed, once they start running, that horizontal speed is added, is combined, and the ball is going faster. But since Einstein discovered, or hypothesized or postulated, now it's been confirmed experimentally, that the speed of light is the same in all reference frames, like we spoke about in session 1 and session 2 of this series. In our example, this does not apply because the light is already going the maximum speed that anything in existence can go through space, as far as we know. So C is actually going the same speed in each of these frames on the ground and in the spacecraft, which means that this vector addition doesn't work with light. You send light up, but you're still moving sideways. The person on the ground looking at it can't add up these velocities. Light is still going C in this direction. Therefore, we have C for tau for the person on the spacecraft, and C for the person looking on the ground. So even though the speed of light is the same, it's actually traveling different distances. So the speed of light is the same, but it's traveling different distances. And thus we have a shorter distance here, which is going to give us proper time. And we have a longer distance here that's going to give us time dilation for the same event. So the same event is measured at takes different amounts of time because the speed of light is the same, but going at different distances, right? That's quite interesting. Which sort of begs the question when you think about it. Um, when the light hits here, right, do they see the light hit at the same time? It seems like they should. And I mean, we have to, of course, take into account the fact that the person seeing the light, let's say we see rays of sunlight. Oh, and I see a chat. Apologize. Let me take a look and see here. Oh, yeah, Lisa, what's going on? Lisa says, "Oh, thanks for saying, Lisa. Thanks. I'm glad you made it." And you said, "Good thing I saw Interstellar movie." Yes, Interstellar is one of my favorite movies. One of my favorite movies. It's awesome. Let me put the timestamps on as well. One of my favorite movies. I've seen it multiple times. And one of my favorite parts is the ending. And of course, the ending only makes sense to the depth that I'm talking about it now after you saw the whole movie. When your girl's laying on her deathbed and she's telling him, I already have people to help me out. You go. And he's like, go where? And she just says, Brand. And the music starts playing. And he's like going out to go meet Brand on the other planet. Like the music and everything. That was awesome. That was like, that and the part where he saves the spacecraft when Matt Damon, who's one of my favorite actors, when he played a villain, played it well, of course. Oh yeah, it is a tear-jerking scene, right? Yeah, it is a tear-jerking scene. I mean, it just so happens that at that period of time, there might be some dust motes flying in the sky or something. But I don't like cry or nothing, but I can't help it if dust is flying around. I get a little watery, that's all it is. That's all that's going on. Just some quantum thing that happens at that part of the movie. But yes, it's a good movie. Yeah. So I'm glad I saw it at the movie theater. But that's one of the ones that, I mean, of course, it's good seeing it anywhere, but seeing it in the movie theater is awesome. It's awesome. Let's keep on going. So now we have the backdrop of why, and I guess it'll be another session talking about why time changes near a black hole. I'll have to look into that more detail to explain that myself. But we can see here in a very simple example with the light clock, the fact that the speed of light it's going the same speed, but is traveling two different distances depending on the observer. Um, and thus we have C with the tau change in time for the person on the spacecraft in proper time, and T for the person on the ground in time dilated time. And we're going to use these three equations to solve for uh, gamma. So let's take a look at how they do it. So earlier we used our triangle to figure this Pythagorean type deal out here. So we're going to start with that. S squared equals D squared plus L squared. So all we're doing is just taking the triangle from the perspective of the person on the ground and squaring it for our time dilation form. And then what we're going to do is we're going to actually solve for, and this is the benefit of going to class, by the way, when you in college, when you're reading a textbook, they do like this because this is a textbook. They cut out some things, so you have to fill in some details. Oh, this was not so hard to fill out, I guess. Just solving for S in one case over 2. Then we'll solve for D in this case. And then we'll solve for L in this case. And again, this is S, the path that the light takes from the perspective of the ground. and with the time from the perspective on the ground, the distance the light takes on the spacecraft with the time of the person on the spacecraft, and this is the distance that the spacecraft travels from the perspective of the time of the person on the ground. Right, so we have two ground times and one spacecraft time. So now we're going to plug this in. So we have z change in t squared equals c change in tau in over 2 squared plus v change in t over 2 squared. Lisa says the mechanical universe had a great video on this light clock example too, but you are going deeper in the math. Sweet, awesome. This light clock is a very, very relevant, even though my relativity class didn't talk about it, but I think it's because we're doing a lot much harder stuff, which I think we'll get to eventually. But a lot of the stuff there I'm still not following myself, so I'm gonna have to go through the textbook again. But it's all tensors and LIGO, and there's just a lot of stuff. So maybe that's why he didn't mention the light clock, because he figured we got it already. But light clock is in my modern physics class, where relativity was a third of the class. He spent like at least a class talking about the light clock and going into a lot of detail on it. So we have this, and looking at the equation, we have everything is divided by 2 and 2 is squared. So we could say t change in t squared over 4 and c change in tau. Forgot to put my paragraph. Squared over 4 plus v change in t squared over 4. And since everything is under 4, we could just drop the 4. And then we have with the, oh, well, the book didn't even number it. Usually, well, I guess it's because that's the work going on. So what we have is c change in tau squared equals v change in t squared minus, I just realized that still have this here. Let me actually move this out the way. Actually, I'll just move this down. Forgot I solved that problem at the end of last session. At least I didn't solve the problem in detail because it's a long problem, but I show the mechanic, the mathematician, in general, my steps for solving this area problem. You can see that in the video last week. All right, so now we have some more room again. That threw me off for a second when I saw that. Where was I? Let's see. And then tau minus, okay, there we go. Boom. So all we did was just subtract v from both sides, and now we have that. Let's look at the book. Did I solve for the right thing? Oh no, let's solve for c. So they're going actually here. What's the best way to maneuver this? Let's simply go just instead of trying to shortcut it, I just start over. Looks like they're solving for, I see. This is the book reverses everything. Oh my gosh, I don't know how to do that. I was trying to look at it from the perspective of a normal equation, how I normally do it. So I would actually put it like this. So there we go. So basically what I have is kind of the reverse of this. So they solve for tau, but instead of putting the tau that they're solving for on the left, they put it on the right. So basically all we have to do is also put this in a proper extra step. We're solving for this right here. So I subtracted v change in t over 2 squared from this side, and subtracted v change in t over 2 squared from this side. On this side, it cancels out. On this side, we have a minus v change in t squared, which is here. And this stays where it's at. And then we solved for this. I just wrote it in the reverse from the book. And it says, finally, solving for change in t in terms of tau gives, all right, so let's go ahead and solve for change in t in terms of tau. Let's see what we get. So let me stop looking at the book because they do it kind of in reverse for me, so it's confusing. And we want to solve for change in regular t. So let's do this. So basically what we'll do is we'll square this. We'll square change in tau squared. And we cancel the 4. So we have c squared change in t squared, cancel the 4, and change in v squared, change in t squared, and we cancel the 4. This will give us on this side change in t squared and c squared minus v squared, because we could basically use I forget the names of all of this stuff now, but what is that? Is it factorization? I think it's factoring. Or the reverse of distribution, whatever the official name is. But this t here is the same. Tau is on the other side. So we could basically extract that t out and just subtract the two things that are multiplied by that t, and it gives us the same answer. And so now I'm going to I'll keep it on the opposite side like the book has momentarily, and say change in tau squared divided by c squared minus v squared, and this is change in t squared. And then we have to do some more algebra on this thing. So let me go ahead and put it back the way I'm used to seeing it. T squared change in tau squared over c squared minus v squared. And the interesting thing about math is you can always multiply everything by 1. So what I'll do is multiply by c squared over c squared. And if I multiply by c squared over c squared, I can distribute this c squared over c squared however I like. So I'll go change in t squared equals, and I'll color code this so it's clear what I'm doing. We have by this. So, and what I'll do is let me make these 2 different colors because I figure that'll still might be a little unclear. So what I'm going to do is this green c squared is on the bottom as in the denominator. So I'm going to keep it in the denominator and put it under this one. And this c squared here is in the numerator. So that c squared is the same thing as if I multiply the numerator by 1 over c squared, the denominator by 1 over c squared. So basically, I'm taking this red c squared at the top, and I'm putting it in the denominator as a fraction, right? So the idea would be, to give an example, let's say I have 1 over 4, and let's say I multiply it by 1 divided by 1 over 2. Well, what's 1 divided by 1 over 2? That's 2. So this is 1 over 4 times 2. So this is the same thing as 2 over 4, right? Which is 1/2. So multiplying by 2 is the same thing as dividing by 1 divided by 2. See that? So multiplying by c squared is the same as dividing by 1 over c squared by that same algebraic logic. So since I did that substitution of my 1 over c squared, the c squared at the top ends up being 1. So since that's just 1, there's no need to write 1 again. So that just becomes tau squared. And I'm going to divide that by distributing this c squared into the parentheses. So that's why I put the parentheses there, to make clear that this c squared over c squared, I'm multiplying it by that entire fraction. So I got to distribute it into the full denominator or numerator, whichever one I multiplied into. So that means I have to distribute this 1 over c squared to both of these. So I'm going to have divided by c squared and divided by c squared. And we know that c squared divided by c squared is 1, like we looked at earlier. So that becomes 1 minus v squared over c squared. And now we see how, well, actually the book did one more thing. So let's do the last thing that it did. So I say we were there. So we have change in t. So basically I could take a square root of all of this. So if I take the square root of all of that, I get change in t on the left side equals plus or minus when I take the square root. And the square root of something squared is just that thing. So then I have change in tau. And the denominator, I don't know what everything is going to be because I can plug in a v for that. So then I just put the square root there. That's 1 minus v squared over c squared. And the square root here, basically, you can write a square root. If you have a square root of a fraction, you can write it over each one individually, and it'll give you the same answer. It's like if we, I'll let you work that one out similar to this way. You guys make up some numbers and plug that in. You'll see that's the case. So now, and I guess the last thing to look at is that time doesn't change in the negative sense. As far as we know, time only goes in one direction, at least with the technology we have. I guess maybe some people in the future might make it go in reverse. So we're only going to take the positive part. So we could say this 1 minus v squared over c squared. And, and they actually put them both in one parentheses. So this is what the book calls problem 5.1, which is, right, is no coincidence, that's the first problem in the book. Now, they call this change in t equals gamma change in tau. So now we have the conversion factor to figure out a conversion between the ground's t, which is here, which is regular t. When I say ground, in our visual example with the astronaut, that's the person on the ground watching the spacecraft go by. And then we have the spacecraft, where the event happens at the same place. Lisa says, a DeLorean with the flux capacitor proves time can be reversed. Facts. I must agree with that. I can't wait till they put those in commercial production. So that'd be even better than Elon's star space. What did he call it? What is it called? Spaceship. I saw a clip. Michael J. Fox and you know what? I never learned that guy's name. He's just a doc, I guess. He's forevermore. He's Doc. So Michael J. Fox and Doc, they appeared on somebody's show. You know how, like on talk shows, they have like guests come on and they do little skits, and they had like some fog come out, like the dry ice fog, and the DeLorean rolled up and it got out, saying it was in the future. But it was happy and it was sad at the same time because you're seeing Doc and you're seeing Michael J. Fox, but they were all old, and Michael J. has the Parkinson, so it was a little bit sad too. I guess some of these people we see, they're people like everybody else, but you wish they could just live forever because they make everybody so happy. It seems odd that they're dying, but that's just the way it is. They'll live on in the movies they made, I suppose. So that's that. So now we got tau. So why don't we look a little bit? Oh, and basically what we're doing is, yes, there are more than movies. It's interesting being able to look back and see some of the actors from back in the day, and you could still see, like now we have so many kid actors. You could see people grow up their entire life. You know, like later when I don't know. Matter of fact, Taylor Lauder, the wolf guy in Twilight, he was a kid actor. I didn't even know that until they showed some. I saw some clips of him on social media recently. They were showing some of his early videos and stuff as well. By the way, we've also split this into two. We see that this is 1 over square root 1 minus v squared over v over c squared, and we just call that gamma, which is this here. All right. So that means that the ground time, we have to multiply this by gamma. And that also means that if we take the ground time and divide it by gamma, oops, we can go this way as well. So we have to look at that. Now, why don't we do for the remaining time, since we got our equation, why don't we just look at some of these, like the relationship it plays here. So this relationship is embodied in these equations. All right, the 4-1 separated. All right, so let's look at this. Let's say now the idea is that V cannot exceed C, but let's say V is 0, right? Let's say the spacecraft is standing still. Let's say the spacecraft is parked on the ground. Spacecraft is parked on the ground, so V equals 0. If V equals 0, then what fraction would you say, Lisa? What fraction or what multiple? Like in other words, if V is 0, and let's say this is alpha, I will just put an alpha variable in front. What value would alpha have if V is 0, would you say? Alpha equals what? And I guess maybe that's not the best way to write the alpha in. Let me write it in a different way. So let's say V equals alpha. Let's say V equals 0. So then we have change in T equals alpha tau, alpha change in tau. And what would you say alpha is? As a fraction of, well, just as it is. 1. Yep, 1. What's going on, sis Hart? Good to see you. I haven't seen you in a while. That's correct. Alpha is 1. So so basically what happened is we'll just put a 0 for V. So it'll be 1 over square root 1 minus 0 over C squared. So this is going to be 1 over square root of 1, and that's 1. So basically we get the same time. So we see that if the spaceship is stationary, then we're going to get the same time in both places. Been caught up, bro. Oh, awesome. Convectors. What are convectors? Hey, sister, I appreciate it. Thanks for letting me know. So it's good to know that. I do see, I can see people pop up once in a while. So thank you for clicking the link, even if you're too busy to drop a line. I appreciate it. Vectors. The covectors. Oh crap. Maybe I should. That sounds familiar. I should know that. Covectors. I'm gonna have to look into it. So I remember hearing the phrase somewhere, but I can't remember exactly what it refers to. Let's look at another one. Let's say that V equals, and usually this is put in terms of the speed of light. And Siddharth says they're from a dual space to help with certain measurements. Okay. Sure, I'll run into it in a bit. The good news, I'll be starting graduate school in the fall. Maybe I'll give a reveal party soon. Maybe I'm gonna have to schedule that, like a reveal stream, which graduate school I'm going to, what I'll be studying. So maybe, I don't know, maybe in June I'll do that. May or June. I'll put that on the schedule. Like, where Daryl's going to graduate school. Yep, for a PhD. I'll be getting a PhD, in physics. I guess y'all know it's physics, but technically it's going to be astronomy, astrophysics. Right. The details will be forthcoming. So maybe I'll schedule that. I'll pick a day and I'll have a reveal. Yep. So I'm graduating this semester with my bachelor's in physics and I'll be continuing on. So I'm happy. Look forward to that. So why don't we look at this one? Let's say V is half the speed of light. Oh, thanks, Lisa. Appreciate it. Thank you both. Yeah, man, I'm glad as well. So graduating strong. I had 2 semesters of honors. You have to make your GPA has to be over 3.5 or 3.6, one of the two, and which is hard to do, I would say, at UT. But I managed to do it 2 semesters. Some semesters I did, but I just didn't have a full 12 hours. You have to have at least 12 credits, which is generally like 3 to 4 classes, depending on, well, actually 4 to 5 classes. Like each class is normally 3 hours, but some of them are 4 hours, so it depends on. Um, but it was cool. So I'll see if I can do it again this semester. A few classes are looking a little bit rough, but a few classes I have an A. But uh, I guess I need to pull up my thermodynamics a bit more. So thermodynamics is ranging like it's like at a uh, between a C plus and a B minus right now. So I think if I pull that one up a little bit, I'll be able to get honors again. So what happens if we put uh, 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 V equals 0.5 C? What would y'all say alpha would be? Change in T equals change in tau alpha. And y'all can try it out. Let me know if y'all see it before I do. I remember myself, it's been a little while since I did this actually. Technically last year when I was in, or a year before when I was in modern physics. We have 0.5 C over C. And this is all squared. So we have, I forgot my square root. Put the square root here. There's a 1/2. So then we have, and all I'm doing, by the way, is just the gamma part. Maybe I'll put it in a different color. So then we have 1 over 1 minus, the c's are going to cancel, and that's why we do it in terms of the speed of light. And of course, that's the only reason, that's the only way relativity matters anyway, is when you're going fast enough that it makes sense to talk about it in terms of the speed of light. Other than that, the effects are negligible. Like, let's say you're going at 0.000001 the speed of light. I mean, it's not really, I mean, it is going to have some dilation, but it's going to probably not even be noticeable, but it can be calculated with these equations here. But then we'll have 0.5 squared. So let me put that in. Oh, well, that should be 0.25. But that's why I remember in class, they always pick round numbers. That's probably why. So half of a half has to be 0.25. And this is going to be the square root of that. So then we have 1 over the square root of 0.75. So now, let's see what the square root of 0.75 is. So 0.75 square root, right? So that's 1 divided by 0.866. Then it gives a 0, so that's a good rounding. Then I'm going to invert this in the calculator. Should be an invert button. I'm actually using my computer calculator here, because I believe my other one is in my book sack. I ain't feel like going to get it because I knew I was going to do some small numbers. And invert button. Oh, there it is. So invert it. That's 1.15. Anybody else got it? Anybody else try it? Let me know if I made a mistake on my math. So that means that now if v equals half the speed of light, change in t, which is the ground time, equals 1.15 change in tau. And now we see why tau is proper time. Because if I solve for tau, we see that tau, we have to divide the time the person on the ground measures by 115 to get the time on the spacecraft. So if the spacecraft, like if the spacecraft is so huge that it takes 15 minutes for the light to travel the full distance from A to B to C. So from A to B to C, if it takes 15 minutes to travel that distance there, right? As measured by the person on the ground, person on the spaceship measuring the light go up and down will measure 15 minutes divided by 1.15. Hi, welcome back to Mathematician. Good to see you. Finishing up this gamma calculation on relativity. And let's see if I can, let's say 15 minutes. That's where I'll just copy it. I'm looking for creative ways to use the same numbers in the calculator, but I forgot you can just copy this thing. So I would divide 15 by that. So the person on the spacecraft will measure only 13 minutes. That's actually a pretty big difference. I mean, 2 whole minutes is off. That's a pretty big difference. So going at the speed of light. Sure, the mathematician. That's no problem. Let's see here. Boom. Welcome. So that means that the person on the spacecraft, if the spacecraft is going with half the speed of light, the person on the spacecraft will measure the light taking 13 minutes, where the person on the ground will measure the light taking 15 minutes. So that's so the time dilation, and actually I might have did that in reverse actually. I think it might be different than, the process might be different going in reverse, but that's the way it gives us a general idea. On a future session, I'll come back and do it in more detail. but this does show us the general idea that proper time is shorter than dilated time, I guess, not only by definition, but simply because, as we can see, utilizing what we learned from the light clock, that because of the conversion factor of the speed of light being what it is, but going two different distances, the stationary observer, meaning the one that's moving with the experiment, will measure a shorter time than the observer that's watching the experiment move. So proper time is therefore shorter than uh, any other time. I guess pretty much they call it like there's proper time, then there's time that's measured by the other observers. And Siddharth says for proper time, d tau and coordinate time dt. Exactly. Let me actually make Siddharth the moderator as well while I'm making some moderators here. That is correct. So, which is very important. So, as we continue, we'll continue to go and fall into this, and eventually, I believe we'll start getting into the actual tensor stuff that my current class is doing right now. But I'm finding that the way it usually is, it's kind of like you don't really understand the class till after the class. It's like now that I'm in quantum two, and of course it helps that I have an awesome quantum two teacher. Like if my quantum one teacher was my quantum two teacher, then I might not be saying the same thing. But suffice it to say, quantum one was hard. And I was thinking, man, quantum ain't for me. But now but I had to take quantum two to get my physics degree. You have to take it. So I was like, okay, I'm going in. I'm just going to do my best. And right now I'm making an A. Right now I have an A in the class. I'm sure there's a lot to do with my awesome teacher who explains very well. And but at the same time, I said all that to say that when I study quantum one, because the stuff that we're doing now is built on the old stuff, which is why I was nervous because that wasn't my best class. So I go back and I study the quantum one stuff to, fill in the gaps for the stuff we're doing in quantum two, but I understand the stuff in quantum one better. So, and I've heard more than one professor say they didn't really start understanding physics until they started teaching physics. Like after they got their PhD, a lot of them didn't start teaching. So it's kind of ironic. This is ironic, but it's to moderate. Let me make sure I didn't miss any. Oh, and Siddharth says, by the way, I always thought about proper time as the local time experienced by a traveler, which is subject to relativistic time dilation, as opposed to coordinate time. But if that's homework, you also uh, no idea if that's how you also think. Well, this is just the official way, like the official way. In the end, it's all just terminology, right? It's just terminology. So long as you recognize that the key is to recognize that if you're traveling with an event, this is the key concept behind it. If you're traveling with an event and you measure that event, if you're traveling with the event, you will measure the shortest amount of time possible for that event. That's really the key concept that this is about. It doesn't really matter if you call it proper time or delayed time or this frame or that frame. It's just if you move with the event, like, let's say, I'm on the Earth, someone's on Mars, someone's on the spacecraft, someone's on another spacecraft. We can pick 100 different observers, right? And Earth is moving around the sun at a certain speed. Mars is moving around the sun at a certain speed. So those are going different distances, and one spacecraft will be going another distance, speed. Another spacecraft can be going another speed. Somebody can be, on a meteor. Everybody can be watching one event, but the person that's moving with that event will measure the shortest amount of time for that event, right? That's really the key perspective that's going on, and everybody else is watching. Everybody else is watching. It might be a challenge to measure what time they measure, but everybody else will measure a longer amount of time. Everybody else will, depending upon their relative time compared to the event. Well, let's say the event is moving at half the speed of light. And let's say Earth is moving in the same direction and Mars is moving in the same direction as the event. So technically, Mars, what are, is Mars, this Mars go faster or slower than us? I guess Mars has to go slower than us because it's farther away from us. So if we're going in the same direction, technically Mars should measure a slower, a longer period of time than Earth. The Earth will measure a slightly shorter period of time, and a spacecraft going at not a quarter, at three-fourths the speed of light will measure a slightly shorter time, but the person on the spacecraft will measure the shortest amount of time for that same event. So no matter what's going on, whoever measures the shortest amount of time that's possible to be measured, that's what we call proper time, at least in the classes I've taken in the textbook I've been looking at. So that's the official way to look at it, Siddharth. Thanks so much. And well, I mean, I guess right now there's no purpose of a moderator right now because I don't have many people. But I plan on continuing. So if in the future we have like 1,000 people in the stream at one time, and I believe you were here that day, Lisa, when either you or it's one of the regulars that was here. It was a while ago now, so I can't remember exactly who it was. But there was one stream I had where this guy came in and just started blabbing a bunch of random nonsense. And basically, that stream, I think I was talking about gravity and gravitation. And the dude was basically saying Newton's wrong and Einstein's wrong, everybody's wrong, I'm right. And he was saying a bunch of stupid stuff like, the photon energy Newton gravity, the photon energy gravity is the spectrum of the right hand of the nucleus of the yeah, and that's the way it works. I'm like, dude, you're just speaking nonsense. No, I know better. And I was like, look, you got to stop putting that stuff in the chat. I mean, he was putting like paragraphs and paragraphs and filling up the whole chat. And it was actually the people watching that was asking real questions. I said, look, you got to stop doing that. I said, look, if you want to talk, let me know. We can come on the stream. If you really know better than Einstein and Newton and everybody, come on and we'll hear what you have to say. But you got to stop doing that. So if somebody did that again, then it'd be cool for the moderators, one of your moderators, to say, hey, you got to stop doing that. I'm going to put you in timeout. But they're going to have so few people that I'll always be able to catch it at this point. But so stuff like that. And she has a lot of chats people write across comments. I'm sure Lisa pretty much took care of it. Catherine did get a little bit toxic. I remember that. It seemed like she was arguing with people. I think she was arguing with me as well. Like you see, I cut my hair because I went and visited one of the cottages, and plus my hair was starting to get itchy. Whenever it gets a certain length, my hair starts itching, so I want to cut it anyway. So I cut it. But at the time, I had my hair and I have my old man bald spot here, and she was saying something like, "What's wrong with your hair?" I was like, "It's just my hair." And she was saying something like, "Oh, you at least comb it or something." Oh, she said something like that, and then I haven't seen her since. So I think she was mad because I was like, you know, that's just my hair. Father Time is my barber. I said something like that. I was just joking. Like Father Time is my barber. It gave me a bald spot right there. And she said something like, you know, she just seemed to be very upset, and she thought maybe she thought I was being rude to her. So I'm just making a lot of the situation. I mean, she did say my hair looked bad, but I didn't take any offense. I just told her time is my barber, gave me my bald spot, but I haven't seen her since. So I don't know. Thanks, mathematician. I appreciate it. Yes, I wanted to get away from the dirt, and I've been much happier. So you can look forward to some science. Try to break it down in the every man's language and in direction, because I mean, really, that's where I can still best learn it as well. And I will, but over time, like right now, we're on part 3 of this. I mean, I imagine maybe we'll get to part 30 of relativity, and we'll be really doing some hard stuff. So we'll see how it goes. Yeah, so I can see it. Yeah, I don't know. Thanks, Lisa. I appreciate it. And mathematician says, just a question. Do you like? I mean, I mean, in this, like, there's a few groups of people who do have a certain identity where it's not racial. So I mean, like I guess technically you could say Indians is a culture, and I like the Indian culture. Like I like the Bhagavad Gita and the Vedantas. Like I haven't really read the whole thing, but I like the idea of it. Like I know the Vedanta, even though I don't talk about it much on this channel, but I'm into like pure non-dualism, and I know the Vedanta is like a non-dualistic text. I looked into it a little bit and saw some of what it talked about. And I always thought the Hindu artwork looks pretty cool. Yeah, and I love Indian food as well. When I lived in Louisville, there was a one of my favorite restaurants was an Indian restaurant. Like the all the people who worked in the restaurant actually uh, 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 came from India. Like they used to rotate back and forth to India. But as far as race, if you mean race, I don't believe in race. I mean, the science is already in. People have already done the genetic work and found out that there's one human race. Like apparently the difference between people in one race, like the demarcations that we call race, are often greater than the differences between people from two different races, as we describe it genetically. You can find a quote black person and a quote white person who are genetically closer than two people who we might say black or two people who we might say white. So race is just, I mean, it's just nonsense. So I see myself as a human being and I see everybody as human beings. And that's just the way I see it. Like even when I applied for grad school, when I just didn't answer the race question, like seemed like all of them, they say you don't have to say your race is just optional for our, um, I don't know, the government asked them to do it so they can like keep a tally. I forget the official word, but I just don't respond. I just don't respond to that question. I'm a human being. I'm not black or white, and I don't see people as black or white or anything or whatever. Everybody's just human beings. So I don't have a problem with anybody for that relation. I'm not religious. I have an idea, ironically, more along the lines of the pure and the non-dualistic. If I was missing it earlier, but not in like not in like a religious belief. That's what I'm saying. I'm biased, but I like Indians. Awesome, guys. Thank y'all for coming. Thank y'all for showing up. It's always good to have some people to interact with. I'm glad y'all like the content, and I think we'll continue with relativity. Since I know all of these topics, like in graduate school, pretty much the four main topics that I'm gonna have to bring to the next level is electromagnetism, classical dynamics, relativity, and statistical mechanics or thermodynamics. So you can look forward to seeing more on each of these. And I'm going to focus on astrophysics, so I'm going to have to do some general relativity. So this will go along that direction as well. So you're certainly welcome. Also, I'll be back next week, and we'll continue on. So now we have gamma. We'll continue from here and keep on going. All right, y'all. See y'all next time.